Welcome DSCPL Sogong aboard. Your learning journey starts now. Ever wondered if a mathematical proof could be audited like a piece of code? What if we could check its structure, its integrity, without necessarily solving the problem itself? That's the core idea behind DSCPL, the Semantic Closure Proof Open Laboratory. So what is this CPL beast? It's an open source system built entirely with Python standard library, meaning you can run it offline right after extraction. Think of it as a three-layered cake. At the bottom, the semantic proof kernel, that's your validation engine, checking certificates against rules U1 through U8. In the middle, problem plugins, these are specific modules for different math problems, like Collatz or Goldbach. And on top, exhibition and audit, giving you a CLI, a static website and report indexing. It comes preloaded with 8 plugins, 6 example certificates, unit tests, and even GitHub Actions configuration. It's designed to be immediately usable and extensible. Now, let's peek under the hood at those validation rules, the U1 to U8 interfaces. These aren't about proving the math true or false, they're about structural integrity. Think of them as syntax checks for proofs. For instance, U1 finite objects ensures everything is well defined, no infinite loops or missing links. U3 maximal relation makes sure every step clearly marks where it ends. U7 extremal preservation checks if key values stay consistent throughout. A pass here means the certificate is structurally sound according to these rules. Crucially, it does not execute the math, nor does it replace peer review. It's a gatekeeper for form, not a judge of truth. So why apply these structural checks? DSCPL focuses on classical open problems like Collatz, Goldbach, Riemann hypothesis, and others. The table shows their classical status, usually open, versus their semantic status within DSCPL. Some, like four-color theorem and Collatz, are marked framework closed, suggesting their semantic structure is considered complete or closed under this system. Others, like Frankel's conjecture or BSD, are candidate closure, while P versus NP remains exploratory. This isn't about solving the problems directly, it's about classifying their semantic closure properties using a defined structure. It's a new lens on old puzzles. Why does all this matter? Because DSCPL draws a clear boundary. Structural validation is distinct from classical certification. It provides tools, a CLI, a static site, report indexing, to exhibit and audit these semantic closure certificates. Getting started is quick. Set up a virtual environment, install, and validate. It's open source, ready for GitHub with automated tests via actions. The future involves pushing it live, enabling those actions and managing licenses. It's a powerful toolkit for exploring the structure of mathematical proofs in a novel way.